Right, so let's look at what happens when we have net force with electrostatic forces. This is an application of finding F net from Newton's laws. The only difference now is we're not using forces like gravitational or weight or an applied force. We're using electrostatic force. All the rules still apply. When I tell you net force in one dimension, that means they're in a straight line. Okay? So here's our example. We have 3 charges, J, which is minus 4 microcoulombs, K, which is plus 6, and L, which is minus 8. They're all in a line, and I ask you to calculate the net electrostatic force on K. What we need to recognize here is that K is going to be attracted to J, because it's negative, and it's going to be attracted to L. Basically, we want to know which of those attraction forces win out. We're going to choose a direction as positive. It doesn't matter. And you can do it at the beginning or you can do it near the end. It doesn't matter. I took right as positive. It may be a good choice. It may not be a good choice. It doesn't make a difference. So, first thing we need to do, so step 1 is we calculate the force between each sphere separately. Make sure I know what you're doing. So here we have the force of J on K. That's what that stands for. I'm using J's charge and I'm using K's charge. Remember, must be in coulombs. So this is minus 4 times 10 to the minus 6. It's micro. 6 times 10 to the minus 6. 8 times 10 to the minus 6. We've got to divide the distances by 1,000. So this is 0.03 meters, 0.06 meters. Substitute everything in that I know. We don't put any charges. We don't put any signs, sorry. And 0.03 is the same as 30 times 10 to the minus 3, which is put in scientific notation. So we get 240 newtons left. I have to put a direction here because an attraction isn't enough. I'm looking at specifically what happens to K. Alright? So K is going to go towards J. Yes, you can say towards J, but left or right is going to be more useful for me in the long run. So that's the force between J and K. Now I need to do the force between L and K. So I'm doing the same thing, and I get 120 to the right because it was attracted to L. We need to now put this in context. So this is what's happening. That was my original diagram. K goes 240 to the left because of J. And it goes 120 to the right because of L. This looks like a diagram we know. That means if I want F net, I'm going to take J, K's force, and L, K's force. I made to the right positive, so if we look back at my diagram, this was to the left, so this is minus 240, because I decided right at the beginning to make right positive. Probably wasn't a good decision. Doesn't matter. I get a negative value. That means it's got to be going to the left. It's going towards J. So nice and simple. When it's in a straight line, you find the 2 forces that are exerted on that charge, and then you either plus or minus them, depending on which direction you've taken as positive. So knowing which direction it's going to move for each individual charge that's affecting that particular charge is very important. You are only going to get 3 charges here. You won't get more than 3. But what happens if we put them at right angles to each other? Well, now, I need you to see all I've done. J was over here. I've just moved it there, so I've got a right angle. Now, I did this deliberately because I don't want to work out this force again, and I don't want to work out this force again. That hasn't changed. So we already knew this, but now, watch here, K is attracted to J. So K is going to move down because of J, and it's going to move to the right because of L. I can't do left, right, positive directions here. So it's 240 newtons down. We calculated the 240 earlier. It's also 120 newtons to the right. Now, this you've seen before. These are forces at a right angle, forces at a right angle. We draw them into a parallelogram. So this would also be where FLK is. F net is the diagonal, which means we're going to use Pythagoras. F net squared is FJ squared, FLK squared, 240 squared plus 120 squared, 72,000. We square rooted 268,33 newtons, but we're not done. We need theta. Okay, theta, tan theta is opposite over adjacent. Theta is 63,43 degrees. So that means we've got 268,33 newtons at 63,43 degrees from LK. Okay, so I know we went towards LK and then we went down. Now you need to do activity 1 on page 209, and you need to do questions 7 and 8.